Okay. Thanks a lot, Joe, and welcome to this third series. So today we have our speaker, Jonathan Moreno. I hope I pronounce it correctly. Who was supervised by Ignacio Negueruela. And our speaker today is doing his PhD thesis in La Plata in Argentina, and he is working on the characterization of massive multiple stars, which means more than 2 stars. And his objective is to obtain the orbital parameters, but also the stellar parameters of the stars, so the mass radii and so on. And he will be graduating next year, so keep updated about his work. That should get out soon. So today is going to talk about, give us an introduction to massive binaries and the classification, detection, and analysis of those systems. So, Jonathan, if you're ready, then I give you the floor.
Okay, thank you. Well, once more, thank you, Sophie, for the introduction. And good morning, afternoon, or evening, everyone. My name is Jonathan Moreno, and I am very glad to be here today. I would like to thank the organizer for inviting me and for giving me the opportunity to share this talk with you. And today I will be talking about the main methods of classification, detection, and analysis used to study massive binaries. This will be a short review intended to give you a general overview of the main observational and modeling techniques used to explore these systems. Well, before we go into details, let me show you what I will be talking about today. The presentation will be divided into 4 main parts. First, I will give you a very brief overview of why massive stars are so important to study. Then we will discuss how to locate and describe binary systems in the sky. And finally, we will focus on the main detection techniques and how the data can be analyzed and modeled. Well, let's begin. For the purpose of this presentation, I will adopt the definition of massive stars as given by Sineker and York. Naturally, these definitions are not universal, and different authors may set slightly different thresholds. But in simple terms, a massive star is an OB-type star that is massive enough to end its life as a core collapse, or a type 2 supernova. The minimum condition for that to happen is that the star initial mass must be greater than about 8 to 10 solar masses. But now, why are these stars so important? Well, first of all, they are the progenitors of compact objects such as neutron stars and black holes. Their stellar and stellar winds and intense ultraviolet radiation have a huge impact in the surrounding spectral medium by shaping it and ionizing it. And finally, they produce heavy elements, which contribute to the chemical enrichment of the galaxies. Another key property of massive stars is their strong tendency to form in binary and multiple systems. In fact, observations show that almost all massive stars are found in such systems. This makes them natural laboratories for studying stellar evolution. Let's take a look at this figure, for example. Along the x-axis, we have the masses of different main sequence stars, while on the y-axis, we show the multiplicity fraction and the companion frequency. As you can see, for massive stars, both quantities approach nearly 100%, highlighting how almost all of them are found in binary or multiple systems. As we will see later, the fact that these stars are found in binary systems allows us to infer parameters that would not be able to obtain if they were isolated. So, to understand how this behaves, if the system behaves, we need to take a look at their basic cinematics. When studying binary stars, one of the first things we need to understand is how the orbits are described. So, in the reference frame of the center of mass of the binary system, formed by 2 stars, one of mass M1 and another mass M2, the shape and timing of the orbital motion are characterized by a set of 6 orbital parameters. These parameters define the orbits in 3-dimensional space. We can divide these parameters into 2 groups. On one side, the semi-major axis, the eccentricity, and the time of pre-electron passages. These 3 parameters describe the size and shapes of the orbit. While on the other side, we have the Keplerian angles, which describe how the orbit is oriented in space. To define the Keplerian angles, we first need to introduce 3 fundamental planes. The first one is the plane of the sky. This plane is always tangential to the celestial sphere. The second one is the plane of the true orbit. In this plane, the orbital motion of the binary takes place. And finally, we have the line of nodes. This line is formed by the intersection of the plane of the orbit with the plane of the sky. And the intersection of the orbital trajectory with the line of nodes define the ascending and descending nodes. Using this concept, we can now define the Kepler angles. First, the orbital inclination is the angle between the plane of the sky and the plane of the orbit. Then we have the longitude of the ascending node. This angle is the angle between the true north and the descending node, and it is measured in the plane of the sky from north to east. Finally, the argument of periastron is the angle between the ascending node and the direction of the periastron, and it is measured in the plane of the orbit from the descending node and increases in the direction of the orbital motion. Well, in an ideal case, like the classical two-body problem with point-like masses, these orbital parameters should remain constant over time and be fully described by Kepler's law. But in reality, however, stars are not isolated point sources, and additional physical effects can cause these parameters to vary with time. We won't cover this topic today. If you find this topic interesting, make sure to follow the next presentation in this series. Well, to wrap up this topic, let's talk about some key equations. Let's start with the relative orbit, which describes how the position of one component changes with respect to the other. Adopting a reference frame centered on the primary star, the relative ellipsis is given by this equation. And this equation gives us the position vector as a function of the true anomaly. If we express this equation in Cartesian coordinates, we obtain this system of equations. And what is interesting here is that all the time dependency is contained in the true anomaly. Well, the true anomaly, theta, is measured in the plane of the orbit, starting from the direction of periastron and increasing along the orbital motion. To describe how the true anomaly changes with time, we first introduce the eccentric anomaly. This is the angle measured from the center of the orbit using an auxiliary side. The relationship between the eccentric and the true anomaly is given by this equation, and also the relationship between the eccentric anomaly and the time is given by the Kepler equation. This last equation plays a crucial role because it links time with position along the orbit. It allows us to move from a uniform time parameter, that means the mean anomaly, to the geometric description of the orbit through the eccentric anomaly. Finally, this symbol we see here is the orbital phase, and we will discuss this concept later on. Well, to understand the motion is one thing, but how do we actually find and classify these systems? Well, let's take a look. Well, binary systems are primarily classified according to the method of observation by which they are discovered. First, we will look at the visual binaries. Well, visual binaries are systems whose components can be individually resolved with telescope. It means that the star must be sufficiently separated, so in general, visual binaries tend to have wider orbits. And the observations relies on direct imaging over long periods of time. For example, we can look at this simple, we can look, to the system from the TUMAS catalog, where the orbit was calculated using images taken between the 2000 and 2004. We can also use the observation of Sirius A and B, for example, as they have a 50 years span with the observations. And well, visual binaries provide a direct way to determine orbital elements such as the orbital period, semi-major axis, eccentricities, and inclinations. And when combined with parallax measurements, we can also get the absolute dimensions and stellar masses. Well, now we turn to photometric binaries. Basically, photometry consists of measuring the variation of flux over time. This is what we see in a light curve. Flux on the vertical axis and orbital phase on the horizontal axis. Orbital phase is simply the difference between the time of observation and the time of the primary minimum. We then divide this by the orbital period and take the fractional part of the result. In other words, the orbital phase is simply the fraction of the orbital period that has passed since the time of the primary minimum. Now, one way to classify the system is by the morphology of the light curve. For example, algol type system displays well-defined eclipses with constant brightness between them, while beta Lyrae show continuous eclipses with only small differences between the primary and the secondary minimum. In contrast, the Ursa Majority system exhibits nearly sinusoidal curves with shallow eclipses. And another way to classify the system is in terms of the Roche potential. In the touch system, for example, the stars do not fill the Roche lobe. In semi-detached system, one star fills the Roche lobe while the other does not. And finally, in contact or over contact system, both stars fill and overflow the Roche lobe, allowing mass exchange. If we focus in a circular system, we can simply write down the conditions under which systems have eclipses or don't. Depending on the combination of orbital separation, inclination, and stellar radii, we may observe one or two eclipses, or not at all. Also, these equations indicate that the large stellar sizes, tight separations, and high inclinations are ideal configuration for eclipses. So, once we are lucky enough to detect eclipses, the light curve itself becomes a powerful source of information. For example, the separation between the primary dips in the light curve provides a measure of the orbital period of the binary. In double eclipse systems, the separation between the primary and the second minima is the period over 2, if the order is circular, right? If any deviation from this timing is clear, if we have a deviation from that timing, that is a clear sign of orbital eccentricity. However, depending on the orientation of the orbit with respect to the observer, not all eccentric systems can be identified that way. For example, we may observe a light curve that looks perfectly circular, while the radial velocity curve clearly shows that the system is actually eccentric. What is happening here can be seen in this animation. In other words, the orbital parameters can sometimes combine in such a way that the eccentricity remains hidden in the photometry. Now, if we define T14 as the total duration of the eclipse and T23 as the time when the other star is completely hidden behind the other, we can constrain the orbital inclination and the relative radii. That means R1 over A and R2 over A, over the semi-axis, using only the shape and duration of eclipses in the light curve. Well, if the system produces a total eclipse, meaning the smaller star is completely hidden, then the relative depth of the eclipses can be directly interpreted as the light ratio between the two stars. And if we could observe the system in two different filters, we wouldn't just get the temperature ratio, we could actually determine the individual effective temperature of both stars. Oh, finally, the shape of eclipses in the light curve can tell us whether the eclipses are partial or total. Total eclipses produce a flat bottom minimum, while partial eclipses look more V-shaped. And one interesting question may be under what circumstances I see only one eclipse? Well, the simple answer is that when the secondary star is much fainter than the primary, right? But a more interesting scenario arises when the inclination, the orbital separation, and the stellar radii combine in such a way that the observer only sees a single eclipse, like this. Due to the specific values of the semi-major axis, radii, and the inclinations, the observer only witnesses one eclipse. Another interesting case occurs when we see photometric variations that are not caused by eclipses at all, but rather by the strong tidal distortion that can affect the stars in a very close system. So, to finish this part, let's take a look at the bias of these techniques, the biases. First, short period systems dominate because stars are closer together, so eclipses are more likely to occur, and long period binaries are much harder to catch. A system with stars of similar masses and thus similar brightness are easier to detect. If one star is much fainter, its eclipses barely change the total light, so we often miss it. And there is also the inclination bias. As the inclination increases, the chances of seeing eclipses also increase. Finally, there is a circulation bias that close massive binaries have circular orbitals due to tidal forces, which make eclipses irregular. So eccentricity binaries at short periods are less likely to be detected. Well, while photometry tells us about eclipses and relative stellar sizes, spectroscopy gives us another window into the system. In spectroscopy binaries, the orbital motion produces a periodic variation in the position of the spectral lines. The amount the spectral line shifts from the laboratory wavelength tells us directly the line of sight velocity component of the start. We then use the Doppler formula to relate the observed wavelength shift directly to the real velocities. In this image, for example, we can see how the centers of two spectral lines are measured after fitting them with two Gaussian profiles. Well, to actually derive the radial velocity expression, we need two steps. First, we take the derivative of the position along the ellipse, and then we simply express that result using Cartesian coordinates. This expression depends on the orbital parameters we discussed earlier, like the true anomaly and the argument of periastron, but they also incorporate the systemic velocity, which is simply the velocity of the center of mass of the system, and introduce a new parameter that we call the semi-amplitude. If we plot a radial velocity curve, the horizontal axis shows orbital phase and the vertical axis shows the velocity of the components. And from this, we can see why the semi-amplitude has its name. It's because it's exactly the half differences between the maximum and the minimum velocity. Also note that in this case, the orbital phase use the time of periastron passages rather than the time of minimum light during an eclipse. Then the radial velocity equations can be rewritten to make the stellar masses explicit, where Q is the mass ratio. And it's important to note that this Q is also equal to the ratio of the semi-amplitudes. Now, with a little bit of algebra, we can derive another useful expression for the radial velocities. What is described here is that the slope of this new expression provides a direct estimate of the mass ratio without even needing a full orbital solution. And the best part is that this result is independent of the model. Well, from this expression, we can see that these systems, or another way, the system will have system with short periods, high inclinations, and larger stellar masses are the ones that will exhibit the strongest radial velocity variations. Well, going back to the original expression for the radial velocity, let me show you how changes in eccentricity and the argument of periastron affect these curves. In this plot, you can see the radial velocity curve showing different eccentricities and arguments of periastrons. Notice that below each curve, you can see the position of the observer relative to the system. And here we can see how the eccentricity changes the radial velocity curve from a perfect sinusoid into a more asymmetric shape. Then the argument of periastron just rotate this asymmetry, changing when the radial velocity peaks or drops during the orbit. So, based on what we actually see in the spectra, we can divide spectroscopy binaries in two main categories. Systems whose spectra only reveal one component are called single-line spectroscopy binaries, or SB1. And an interesting way to look at SB1 system is with dynamic spectra. Here you can see a series of spectra plotted by wavelength and orbital phase. The contrast between the dark and bright regions correspond to the presence of spectral lines. So what we observe is that if we focus on a particular spectral line, we see its wavelength changes over time. These variations correspond directly to the star orbital motion, and that is precisely what we are seeing in the radial velocity plot on the right. Now, for SB2 systems, we can see a spectral line from both stars, which let us track the motion of each component simultaneously. In the image below, you can see two spectra of the same system at different orbital phases. The orange lines belong to the primary star, and the green lines to the secondary. You can see how one set of spectral lines shift toward shorter wavelengths while the other moves toward longer wavelengths. This process is what causes the radial velocities to increase or decrease. And this fits nicely with the radial velocity curve, where the velocities of both stars are anti-correlated. Well, since we can only measure the semi-amplitude of the primary star in a SV1 binary, we face a limitation when trying to determine the masses. We can overcome this by using the mass function, which allows us to estimate a minimum mass for the unseen secondary star. Moving to SV2 systems, here we can measure both semi-amplitude, which is key to finding the mass ratio, and with this information, we can estimate the minimum masses for each component. And it's important to note that the minimum masses, the main important part here is to know that the minimum masses are called that way because as the inclination is unknown, we are restricted to a lower limit of the true masses. And now let's consider the mass function itself, because the mass function is always less than the minimum masses. So using the mass function gives us a weaker constraint than the minimum masses and usually underestimate the secondary star masses. In other words, the SV2 system provides stronger constraints on the stellar masses than the SV1s. Okay, to close this topic, let's see what kind of biases we find in spectroscopic binaries. Well, low inclination systems produce only small radial velocities, making them much harder to detect. Then, long period binaries have much lower velocity changes, which means that they require long-term monitoring. For SV2s, a faint secondary can be missed, making the system appear as SV1, and higher masses systems are easy to detect because they induce larger velocity amplitudes. Finally, limited spectral resolution can blend lines, especially in SV2s, making it difficult to separate the components. Now, let's move on to astrometry. Astrometry deals with the precise measurement of the angular position of a star on the sky and how these positions change over time. When we look at a single star, this apparent motion on the sky is the result of two different effects. First, there is a straight line motion called proper motion, and second, the parallactic motion caused by the star moving around the sun. Finally, the sum of these two motions will produce the total observed motion of the star on the sky. Now, if we consider a binary system, the combination of these two motions produces the pattern you see in this video, which is exactly what the missions like Gaia have observed. To follow the angular motion of the system over time, we simply track the position of the photocenter and see how it changes on the sky. The photocenter is essentially like the center of mass, but instead of being weighted by the star masses, is weighted by the star fluxes. To understand why this is important, let's look at this image. In this, for example, we see a planet orbiting a star, and because the planet barely contributes any fluxes or masses, therefore the center of mass is basically coincides with the photocenter. In the second case, we have two stars with nearly equal masses but different fluxes. So the barycenter lies halfway between them, but the photocenter is closer to the bright star, that means the yellow star. As a result, the photocenter will orbit the barycenter, tracing an ellipse with the semi-major axis called A0. Here we can see the same idea illustrated in a plot of ray ascension versus declination. This is just to see the difference of the barycenter to the photocenter. Now, let's talk about what are the main observables in astrometric binaries. In this technique, we actually measure the changes in the position of the sky. We can track the angular position of the system over time, usually the position of the photocenter, and see how it varies. And also we can detect the proper motion, also the annual parallax, and on top of that, the small periodic wobble of the photocenter produced by the orbital motion around the barycenter. Then, by fitting the motion of the photocenter across the sky over time, we can derive We can derive parameters such as the periodicity, eccentricity, inclinations, and arguments of periastron, and the apparent major axis. Well, now let's move on to another technique that also resolves closed systems. That means interferometry. That there is this technique basically recombines the light collected from different telescopes in a coherent way. Coherently meaning that the light waves are combined while preserving their phase information, which is essential to measure interference patterns and extract spatial details. According to the Rayleigh criterion, the minimum angular separation that two sources can be distinguished depends on the observing wavelength and the telescope diameter. Here we can see how the ability to resolve two sources depends on the angular separation relative to the telescope resolution limit. When the separation is larger than the Rayleigh limit, both sources are clearly distinguished. And at the limit, the refraction pattern starts to overlap, and then the separation, when the separation is smaller, the two objects appear as one. To overcome the Rayleigh limit, interferometry combines light from multiple and wide space telescopes. The distance between these telescopes, called the baseline, simulates the diameter of much larger telescope. By replacing the physical telescope diameter with the large baseline in the Rayleigh criterion, we achieve a dramatically higher high angular resolution. In this example, we show how the Mona Lisa would appear when observed with antennas in different orientations. When the antennas are aligned along a single direction, like horizontal or vertical, we can only resolve details along that line. By combining baseline at multiple angles, we recover a more complete image. In interferometry, the resolution is determined by the baseline and not the size of individual antennas. The larger the baseline, the finer details we can resolve. In this example, with the ALMA ray, as the antennas are moved farther and farther away, more details of the Mona Lisa become visible. However, beyond a certain point, only the very fine details remain. While the larger structures, like the separation between the sky and the figure, start to disappear as their interference patterns wash out. With this technique, we can directly resolve the individual stars in a binary system. From the images, we measure two key observables. The angular separation, which tells us how far apart the stars appear in the sky, and the position angle, which tells us the direction of the secondary relative to the primary. We also measure the flux ratio between the components, and by tracking this position over time, we can fit the orbit and derive all the main orbital parameters, like the period, eccentricity, inclination, argument of periastron, longitude of the ascending node, and the true semi-major axis. Overall, the key feature of the interferometry compared to astrometry is that we get the true relative orbit and the direct flux ratio, not just the motion of the photocenter. So, to finish with this section, this table I will show you summarizes what we have been discussed about the different observational techniques. Here we can see that each method provides access to a different projection of the orbital motion. For example, spectroscopy gives us a motion along the line of sight, while visual and interferometry observation give us a motion in the plane of the sky. As you can see, none of these techniques alone can provide the complete orbital solution. But when combined them, we can recover the full three-dimensional orbit. And that's the key to get the absolute masses, radii, and distances. And that's why multi-technique studies are so important, because the combined data is what let us see the full picture. Now we have seen the main observation method for massive binaries. Let's move on to how we analyze the data. Of the many tools available, I will focus on three essential ones. The first will be we are going to explore is a periodogram. It's a tool to find periodic signals in time series data. And at the heart of the periodogram is the Fourier transform. it decomposes a time domain signal function into its frequency components. This allows us to see which frequencies dominate the signal and which are responsible for the observed periodicity. In this animation, we can see how the Fourier transform takes an input function in the time domain and converts it into a new function in the frequency domain. In other words, the original function in red represents amplitude as a function of time, while its Fourier transform in blue represents amplitude as a function of frequency. In astronomy, we rarely use the continuous Fourier transform, and this is mainly for two reasons. First, observations are usually irregular space in time, and because this happens because of clouds, daytime gaps, or telescope scheduling. And second, the classical Fourier methods assume uniform sampling, so they fail under these conditions. To deal with irregular sample data, we use the discrete Fourier transform, whose classical periogram is simply the square modulus of this function. However, in astronomy, we usually rely on the normalized long-scale periogram to handle uneven space observation. This method allows us to detect periodic signals even when the observations are uneven spaced in time. For instance, this plot illustrates the magnitude variation as a function of Julian date. And as a result of this method, we arrive at this other plot, which is the periogram itself. On the horizontal line axis, we can observe the period or the frequency, while on the vertical axis, we measure the strength or amplitude of that periodicity. What this initial plot reveals is that the highest amplitude or the strongest period is located within the range of 0 and 0.5 days, for example. And by performing a detailed zoom in on this specific region, we can precisely determine that the best fit for this data will be a period of 2.8 hours. Finally, using this period, we can phase the data and generate a folded light curve. With the folded light curve, although the light curve looks pretty good with this period, it should be noted that the use of periogram is merely a starting point. This value is typically used as initial input for further and more detailed fitting programs. Now, let's talk about the disentangling. Basically, this technique allows us to recover the individual spectra of each star, from the combined line of the system. The problem here is that in some closed binary, the spectral lines from both stars are so blended that it becomes really difficult to measure them individually. The goal here is to recover the individual spectra of each star and the radial velocity curve from a set of composite spectra. The idea of this method is to separate the stellar components in a cyclic process. We achieve this by repeatedly subtracting one star contribution from the combined spectrum and to isolate the other, continuing this cycle until both individual spectra and their respective velocities are recovered. In this plot, for example, the combined spectrum is represented at the top, while the individual spectra for each component are displayed in colors. Well, after period analysis and spectral disentangling, we often need to model the system in detail. This is where Phoebe comes in. This is a software designed to simultaneously fit the photometric, spectric, and astrometry data. With Phoebe, we can derive a wide range of stellar and orbital parameters. And for the standard source, we can estimate masses, radius, temperatures, luminosities, and even the gravity distribution across the surface. Regarding the orbit, Phoebe allows us to determine inclinations, eccentricity, and the orientation of the system. And more advanced features include spin orbit misalignment, rotation, and tidal distortions. Although Phi1 is no longer under active development or maintenance, it possesses a highly intuitive and friendly user interface, which you can see below. A practical recommendation, and at least a personal recommendation, is to start with the Phi1. And once you have obtained the parameters you're looking for, you can use them as an input for PV2 to take advantages of his more advanced modeling capabilities. As a practical example, I can briefly show you the eclipsing binary system that I'm currently fitting with Phoebe. And for this specific model, we are utilizing both photometric data in two filters and complementary with the spectroscopy data. On the other hand, PV2 represents a complete redesign of the original PV code. It is written entirely in Python, which makes them modular and flexible. And the new version also provides much better numerical accuracy with advantages like the surface discretization, line darkening, and reflection models. Also, it's designed to handle modern and high precision data, like the data from the missions of Kepler or TESS. And finally, it includes a powerful visualization tool that is actively maintained. Well, to conclude, I mean, the main result and ideas that we were talking about can be summarized as follows. We have seen that most massive stars are found in binary on multiple systems. Also that some orbital parameters describe the geometry of the orbit, while others the orientations in the space. And that there is no single observation technique that can provide all orbital parameters. Different methods must be combined. And finally, modeling and fitting tools are essential to achieve a consistent description of the system and to derive more precise measurements. So, well, that's all. Thank you.
Thank you very much, Jonathan, for your fantastic overview. Do we have question in the audience? You can raise your hand or a lot of applause. I see. Well, maybe I can take the opportunity of sharing this to us the first. Oh no, Sergio, please go ahead.
Okay, thank you very much, Jonathan, for this very nice and complete overview on observational aspects on binaries. So I wanted to ask you something, and also maybe we can open for discussion in the audience, you as an expert on binaries. So when we talk about SB1 systems and SB2, this is a question that the borderline between the two is a bit, sometimes it's not so easy. So what is, in your case, in the case of your group, and then later we can ask the same for the audience, what is making the difference when you say it's SB1 or SB2?
Well, basically, when we can detect the signal of one star or the two or the both stars, basically. I mean, I don't know if I have a case here to show you, but I see your point. Maybe when you see
so at the end, it will depend on the quality of the data, the number of spectra you have. If you then go, for example, this goal is because it's a discussion I have already had with some people. So if you use this entangling and then you detect a companion, but you don't see the faint companion in each of the spectra, is this a SB2 system or no? It's something that...
No, as I understand, if you don't detect the companion in the spectrum, you cannot say that it's SB2. You have to remain with the SB1 assumption.
And normally, what is the difference in magnitude between the two stars that where you can see or not the companion? Is there any number on this or?
Is there any number? I'm sure there is, but right now I don't get that number in mind. Sorry.
Yes, Thibaut?
Thank you, Jonathan.
Thank you.
Hello, thank you for the talk. Just to try to maybe a bit answer in more detail, actually you can have unresolved SB2, right? Because when you say that we cannot detect them, actually you can also use composite spectra to try to unravel the presence of the companion, even so you cannot see the radial velocity variations. And so we can coin them kind of unresolved SB2 that it will appear as an SB1 if you don't make this kind of composite spectral fitting to try to uncover them. And also you have a sensitivity to the wavelength range. So basically when you are observing in infrared region, then you are more sensitive to lower mass ratio, right? Because you are going towards the red part of the black body, right? And so the contribution of the secondary start to become more significant compared to UV region, right?
Mm-hmm. Right. Yes. Yes, very good point. Yes.
Yes, Jesus.
Yes, actually, Sophie asked me to answer the previous question. Anyway, yeah, so one is an SB1 and one is an SB2. I mean, what Jonathan said is basically what is correct. The question is, when can you detect the secondary? It depends on many things. It depends, of course, the most important, as you mentioned, is magnitude difference, but also depends on velocity difference, whether it's a fast rotator or a slow rotator, and what is your signal to noise. So one thing that is becoming more common now that we have these disentangling tools is that, okay, so you have an SB1, you don't know if it's an SB2, so what you do is you try with the disentangling to assume different mass ratios. So you assume different mass ratios, and you see if you can get a coherent answer from a hypothetical SB2 companion. So, and you try different values of the mass ratios, and sometimes you find nothing, and sometimes you find it because one of the advantages of disentangling is that it allows you to accumulate signal to noise by adding many different exposures. So it's possible that it's not obvious in any of the individual exposures, but once you apply disentangle, this can become. And this has been used in a number of cases to actually detect companions that have several magnitudes of difference. But of course, the result you get is I mean, not ideal, but at least you get a mass ratio.
Mm-hmm.
Sergio?
Okay, so this is exactly the kind of discussion I wanted to have, and just since this is more kind of lecturing thing and it's a legacy for the future, I think it's important to take all these things into account for the interpretation of results presented in paper, especially now that we are not going to detail analysis of binaries, but we have large surveys and all this. So we have to be very careful with combining results, saying this is SB1, SB2. So please, people, be careful with understanding what does SB1 mean, SB2 means in the different papers to avoid misinterpretations in terms of percentages of SB1, SB2s, and all this. So this was the reason of my comment.
Yeah, I mean, just to follow up, I mean, and you can, when you do this in the paper, of course, you have to be careful, but sometimes you can have different nomenclature, meaning, okay, so let's say you have, I don't know, 30 or 40 epochs of an system, and you see clearly that it's an SB1 and you can measure it. And then in a few of those epochs, you see the secondary companion. What you can say in those cases is that the system is an SB2, but you can only provide an SB1 orbit, right? So there you're making a difference between what is the nature of the system, right, and what you can do. Because then there is with SB1s there is always the question, and this is of course a hot topic, of whether you see the companion because your data is not good enough, or you don't see the companion because you cannot see it. Of course, meaning, so putting a question, is the companion a low mass star, or is it a black hole or a neutron star? In the first case, you basically don't see it because, well, the magnitude difference is too large, but eventually you can think that if your data had an incredible high signal to noise, you could detect it, while in the second one, you can't.
Very good point. Do we have other comment about that, or do we have other questions? Yes, Michael?
Hi, this was a really great talk. I just have one kind of comment/question. At some point you mentioned about being able to see only one eclipse or being able to see multiple eclipses. And I think you mentioned that you can do that depending on kind of the orientation, but as far as I understood, the only way to get a single eclipse and not seeing the secondary is if you have some sort of eccentricity in there, and I'm not sure if you mentioned that, so I just wanted to clarify that point.
Yes, I think I mentioned it. Let me see. We can get the slide I want. Yes, here you can see the screen, right?
Yeah.
Now, what I try to mention here. Oh, you're right. I didn't mention the eccentricity here, but yes, it's a factor to that will have effect on this. Yes, but also what was interesting here is what I mentioned, that this is a particular case where all the orbital parameters combine in such a way that produce this particular geometry, right?
No, of course, but I mean, the important thing here is that the system is eccentric, and that in a circular system, you would never get a case in a circular system where you only have one eclipse. Is the only point that I'm trying to make.
Let me think about it. Yeah, I think you're right. If I'm thinking right now, I think you're right. Yeah, because the closer because I am thinking that what is most important here is the semi-major axis and the radii. But if you have a circular orbit,
Yeah,
no, I think
Jonathan, I think the best way to see it is that in order for Michael is correct. In order for that to see that, you have to see that the two distances have to be different. And you can only get that if you have an eccentric orbit. So the two distances have to be different.
Yeah, thank you. Yes, I see it now. Thank you.
Okay, Joe?
Yeah, thanks a lot for this very nice talk and overview. I have a question. Maybe you cannot answer it, but maybe somebody else in the audience might be able to answer it. So I'm certainly not at all a specialist on binaries, but to my knowledge, when one is analyzing the parameters by means of photometry, then it seems to be important to use the correct limb darkening law in order to reproduce the shape of the minima. So my question would be, what would happen or what is happening if on the one side one is using more or less a completely correct limb darkening law, and on the other side one is completely neglecting this? So are the errors large, or is it only a small correction, or what comes out? Maybe somebody else has already played with this in these codes.
Yeah, I can mention. So, for example, if you change your limb darkening law from linear to logarithmic, for example, we know that for example, logarithmic better fits or better represents what's happening with the star. The difference you get in the actual light curves are fairly small in most cases. So I mean, it shouldn't have a huge effect, but it is still important to get it right because I mean, with how small you can get your errors with the light curve, or sorry, with a fit with your light curve and your radial velocity curve with a combined fit, if your limb darkening law is wrong, yeah, you're on the limit where that can make a difference. But I mean, in terms of the shapes of the light curves, it's going to be small.
Yeah, that might be correct, but just speaking from the typical errors, which so for instance, for your case, so even if you can reproduce the light curves with two limb darkening laws, what would be the typical differences then in the parameters of the binary? Is it a 10% effect? I have no idea, or is it a 1% effect, or whatever?
I think it's on the small side. I mean, I wouldn't put it up to 10%. I mean, I would say you'd be moving around within your error box. So like
okay.
it wouldn't be several sigma away or anything like that. I think
Okay.
a more kind of a more important issue here is the gravity darkening law and the way that we handle gravity darkening, because especially if you have distorted systems, that's quite wrong usually
Yeah.
in the codes that we're using. So.
Yeah, but that shapes everything, gravity darkening, when you have certain effects from those. So thank you.
And Joe, just to continue, I mean, this is what the cases here are. Let's say the normal cases. Some peculiar cases, you can have light curves that are even more complicated. I mean, you have additional effects. You can have reflection effects. So you can see when you have a hot star and a cool star with different, you can see how, depending on orientation, you are seeing the reflection of the hot light on the cool star. You can also see in some cases, when you have eccentric orbits, you can have heartbeats, right? Which means that at some point near periastron, you have a change, which is due to something that happens to the star due to the interaction. And we even have some cases in which an eccentric binary excites pulsations. So you have pulsations that are in phase with the orbit. So that means, that of course they are multiples, right? So you can have cases in which for example, you have the light curve, and then you have something that is 7 or 8 times, which is one of the fundamental frequencies of oscillation of the star, but is induced by the eccentricity. So you can have even more complicated light curves. And I'm with Michael that of course you have to model the limb darkening, but sometimes there are other more important effects that you have to worry about.
Okay, thank you for this discussion. Maybe I can take the privilege to ask a question also. Maybe it's too detailed, but someone can answer to that one. So what are the pros and cons of doing the disentangling in the Fourier space or in the wavelength space? Sorry for my question.
No, I think the main problem here will be the signal loss relation. I mean, when you make the disentangle, you're gonna lose some of the some of the signal. But I think someone in the audience maybe correct me.
Yeah, maybe I can specific a bit my question, or we can move on. But there are two methods of doing disentangling. You can either do it as you have presented it, or we can also move on to the Fourier space. And I was wondering, what are the differences between the two methods, and what are the pros of using one or rather the other, or if there is no difference? I was maybe expecting Michael to answer, but
yeah, I mean, I've used both. Theoretically, there shouldn't be a difference in terms of the solution that you get out. They should get you to the same answer. Sometimes one behaves better than the other. It really depends on your specific system, how much data you have, and all of that. So, in terms of which one is better, I don't really have an answer. Yeah, it's not a very satisfying answer, unfortunately.
Oh, but that's an answer. Thank you.
Yeah.
Do you have other question in the audience? Yes, Thibaut.
Yes, I would like to come back to this case where you have an eclipsing binary showing only one eclipse, right? I do not understand why you can't have this also in a circular orbit, because the very example which is given on the right panel here could be actually circular. And that's, for me, will work as well, right?
No, because it's symmetric, right? So I mean, if it's completely circular, then and you assume that you are infinitely far away, which is a decent enough assumption for these stars. In a circular orbit, if you have one covering the other at one phase, then at the 50% phase again, you're going to have the same.
This is only true if the mass ratio is 1, but now if you have a different mass ratio, then you will have different distances. And I
No,
think that you
if
can
it's
have
the distances won't change in a circular orbit.
no, but
The distances between the two stars.
but the projections will not make an effect here?
No.
No?
No.
Okay, interesting. I have to think in more
Yeah,
detail. Thank you.
Yeah, the only way for you to get them to not eclipse is if the distance between the two stars change, or the radii change.
Yeah.
But we're assuming that both of those are constant here.
Okay. Thank you.
Do we have other questions, comments, discussions? No? Still not? Okay, then I think we can thank the speaker again, and we can also thank the audience again for this very interesting discussion afterwards. And we meet next week for the second talk.
Thank you, everyone.